Here are solutions to homework set number 11 for ECE 376. This homework set looks at serial ports and Z-transforms. The first problem is to input a number on the serial port, or if you don't have a serial port available, some other input, and from that generate a precise frequency. So I do have a serial port, so here's what I'm going to do. Type in a number like 1, 2, 3, enter, and what appears over here is the frequency. It's 123, and there's the frequency, 123 hertz. If I go back and type in the number 456, enter, what appears on the screen is now 456 hertz. So how do I make that work? Well, in terms of flowcharts, I'm actually using 3 different interrupts in the main routine. Timer 1 is running because I'm using capture 1 interrupt. Timer 1 just keeps track of time. Timer 1 compare sets up the next interrupt and then toggles a pin. Then the serial port sits there and watches for the keystrokes. If I type in a number like 123, saves it in a buffer, when I hit enter, it copies the data, sets a flag. The main routine then looks for that flag, and if you see it, parse the data to see what the frequency is, like 123, calculate the number of clocks between interrupts for that frequency, update the display, and repeat. In terms of coding, here's the interrupt service routines. Again, timer 1 doesn't do much. Capture 1 toggles every n clocks. The serial port takes the data that I'm typing, throws it into a buffer called message 0. When I see a carriage return, that's ASCII 13, copy message 0 to message 1, and set a flag. The main routine then, so this is set it up, turn on the interrupts. Main routine, I look for the flag. If the flag is set, I will parse it. So the message is parsed as ASCII, everything's ASCII, which is why I subtract 48. ASCII 0 is actually 48. 100 digits, 10 digits, 1 digit, that becomes hertz. Calculate the number of clocks between interrupts, then exit. And again, what happens, repeating that, if I type in a number like 627, enter, or not, it's not going to expand for me. If it did expand, you'd see it at 627 hertz. Try another one, 111, and I'll show you some more examples, but apparently Screencast-O-Matic and Hyperterminal do not play well together. Not surprising, Hyperterminal is a really old program. But anyway, if it did work, this is what you'd see. Type in the number 123, and that's the frequency that appears. 456, here's the frequency you get out. 987, here's the frequency you get out. So that's one way to get data to your processor through the keyboard using serial port interrupts. Again, just an input. We've got many ways to get data to your PIC chip. You can use the analog input, push buttons, keypad, optical encoders, keyboard, many ways to get data to it. So switching gears. The next topic we're looking at are digital filters. With a microprocessor, you actually should be using the Z-transform. The Laplace transform is designed for the continuous domain. Think capacitors, inductors, where you're satisfying differential equations. The Z-transform is for difference equations. Think microprocessor. Problem 4 looks at a differential equation. If I have a transfer function in S, what that means is cross-multiply. Sy means the derivative of y. The Laplace transform assumes everything's in the form of e to the st. So when I take the derivative, I get s, e to the st. So differentiation is the same thing as multiplying by s. So this is notation that means the second derivative of y plus 4 times the first derivative plus 20 times y is 2 times the derivative of x plus 30x. So this differential equation is the same as that transfer function. Just different ways of writing it. The reason we like transfer functions is it makes analysis much easier. Suppose I have x of t is 2 plus 3 sine of 4t. I can use superposition to treat this as 2 separate problems. If x of t is 2, find y. if x of t is 3 sine of 4t. Find y. Then by superposition, the total answer will be the sum of the two. So starting out, if x of t is 2, s equals 0, again everything is e to the st. If I have a constant, s equals 0, e to the 0 is 1. X is 2. This is the gain everywhere. All I care about is what's the gain at s equals 0 times the input at s equals 0, and I get a number, 3. What that means is y of t is 3, a constant. Second half, if x of t is 3 sine of 4t, s is j4, x is 0 minus j3, and the real part is cosine, minus j is sine, so this represents a sine wave, amplitude 3. Here's the gain everywhere. All I care about is what's the gain at 4 radians per second, times the input at 4 radians per second gives you a complex number. The real part means cosine, minus j means sine. Put the two together, and here's your total answer. It's the DC term plus the AC term. So again, that's using the S domain, a differential equation. With microprocessors, we use the Z domain. So if I have a transfer function in Z, what that means is, again, cross multiply. In the Z domain, the assumption is everything is in the form of z to the k. So when I find out what is y of k plus 1, I get z times z to the k. So times z is the same as moving forward in time by one sample. So z squared is moved forward in time 2 samples. Z is moved forward in time 1. That's just y. X moved forward 1, x. So here's your difference equation that corresponds to that transfer function. If you don't like future values, I can do a change in variable or a time shift everything by 2, and this is also valid. Either equation is correct. They're both perfectly valid. So in the Z domain, I actually have a difference equation, not a differential equation. It's still a filter. If my input is a constant and a sine wave, the output's a constant and a sine wave. To solve, use superposition. If the input is 2, then at that frequency s equals 0, the conversion from the s-plane to the z-plane is z is e to the st. Plug in s equals 0, I get 1. X is 2. This is the gain everywhere. I want to know what's the gain at DC. What's the gain at z equals 1 times the input gives you a number. If the input is 3 sine of 4t, again s equals j4, z is e to the st. My sampling rate was 0.01, so this is e to the j 0.04, or 1 at 0.04 radians. X is 0 minus j3, 0 cosine, 3 sine. To find y, here's the gain everywhere. This is the gain everywhere. I just want to know what's the gain at 4 radians per second times the input at 4 radians per second. Put it all in, I get a complex number. Real part's cosine, minus j is sine. Add the DC and AC together, and I get the total answer. So in the Z domain, it's similar to the S domain. Sine wave in, sine wave out. It's a filter. If I want to find the step response, well, this is actually a different problem. The previous answer was actually phasors. If the input is a sine wave, the output's a sine wave. I just need to know the amplitude and phase shift, or sine and cosine term. If the input is 0 for t less than 0, then turns on. That's actually a z-transform problem. To solve, I replace x with a z-transform. That's 2z over z minus 1. That's the z-transform of y. Take the inverse z-transform. A couple ways to do that. One is pull out a z, do a partial fraction expansion, multiply through by z, and now I can use my table. This is 78 e to the 0.8k, 78 times 0.8 to the k, plus 26 times 0.5 to the k, plus 52 for time positive. So the trick is kind of pull out a z. If you don't do that, I'll get the correct answer, but in a different form. If I don't pull out the z, I can still do a partial fraction expansion. But the problem is I don't have a z. If you look at the z-transform tables, I've got a z in the numerator, so multiply both sides by z. I can now take the inverse z-transform. There's the first term, second term, third term. This is z times y. Divide by z. Dividing by z is delay by 1. So take all these, delay them by 1, k goes to k minus 1, and you have a second form of y. They're both equivalent, just different way of writing it. And that is homework set number 11 for 376. 333.